Hello everyone! Today we'll talk about the solution to the problem count the number of fair pairs. This is a nice problem with a concise statement that will showcase two common patterns in problem solving, which if you're familiar with you probably see immediately, and if you're not familiar then this is a nice educational opportunity. First pattern, I'm not sure if it's even good to call it a pattern, is that when we have something of the form like this, where we have pair of indices ij, I is smaller than j, and we are looking at in this case, a sum of the ith and jth value. And when it comes to there being a sum, it doesn't matter if we sum the first one and then the second, or the second and the first. Then that essentially counts the number of ordered pairs. So we don't really have to think about the fact that I is less than j, or at least we don't have to think about it too much if we don't want to, because this just tells us how many pairs of numbers there are, such that the two numbers are on different positions, so we can't count the same number twice, and the fact that I is less than j, it just enforces every pair to be counted exactly once. So this is really for our convenience typically. So this is the first pattern. And the second pattern, which might be useful, or maybe it won't be useful, is that, and of course I'll use it in my solution, but I'm not sure that it's necessary, is that when we have to count the number of pairs that satisfy something from both sides, so it has to be less than or equal to upper, but also more than or equal than lower, then what we can do, if it makes things more convenient for us, is to only implement one side of that inequality, and then just solve the problem twice and subtract the results. Because the number of pairs that satisfy this, of ordered pairs, is exactly the number of pairs that satisfy only the right inequality, less than or equal to upper, minus those that satisfy the inequality less than or equal to lower minus 1. Right? So, and it's very natural to think about that, because we want our pairs to be not greater than upper, but also greater than or equal to lower, so we can take all that are less than or equal to upper and subtract the number of those that are at the same time less than lower, less than or equal to lower minus 1. So this is the second pattern. And the third thing that will probably be pretty obvious is that it's probably a good idea to sort the array. And this goes back to the first pattern, where since this is just the number of ordered pairs, then the number of ordered pairs, while it's ordered, we don't care about the order of the elements next to each other. So if we can rearrange the elements however we want. I guess that is the most important part of that pattern. Because if two numbers are a valid pair, then they will be a valid pair even if they are swapped around. Then just I and j will swap. We'll not count them the way we'll be counting them in the original array, but we'll be counting them in the second opportunity when I and j have their places swapped. So, in other words, we can just sort the array and somehow solve the problem for only one half of the inequality. And finally, to solve the problem for a single part of inequality, which is the final part of the puzzle, we can notice the fact that if we have some set, let's say left or right end, so the jth value, then what are the correct left values, the correct smaller values, ith values? Well, there will be some cutoff point, let's say to the left of our element, where everything here will create a good pair, the sum will not be too big, and everything to the right would give us too big of a sum. So just the number of elements in this portion is the number of good i's for this j, and the sum over all j's of the number of good i's is just the number of good pairs. And of course we have to keep in mind that this cutoff point, it might appear for instance to the right of this element, and we only want to count i's up to and not including our element, because we do not want to take our element twice, this is illegal, and we don't want to take our element and some element to the right, because we have already counted that pair previously. We have counted that pair when the jth element is that element to the right, and our element is the ith element. So at that point we have counted it. So this is one thing that we have to keep in mind. And that allows us, of course, to use a simple two-pointer technique on this sorted array. We'll be let's say in my implementation, pushing the right end to the left. We'll be maintaining the left end and pushing it to the right. And at every point, we just know the size of this prefix to be the number of good pairs for this right end for this jth element. So we sort the array, and we have a helper function that counts the number of pairs whose sum is less than or equal to upper. So the final result is go of upper minus go of lower minus 1. So this is what I said previously. And to count it using 2 pointers, we maintain the current result. We maintain the left end at variable I. So variable I will be pointing to the first bad value. For the first element we cannot take to create a pair. We'll be getting our right end j from the right to the left. And now, if we take our limit, our upper, and subtract the value of the jth element, then this is the highest value that our element I can have, so that the sum is still less than or equal to upper. So we'll remember this limit. And while I is less than j, and while the value of nums of I is less than or equal to the limit, so this value is a good pair with our jth value. We push the I forward, right? Because I will want to point to the first wrong element. And we add to the result after this push the number of good elements. So this is essentially I. Because if I is equal to 3, that means that it's pointing to the fourth element in our array, and the first 3 elements in our array are correct. And of course we want to take the minimum of that and j, because we only want element to the left of j, and in that case this will be a correct, after going through all the j's, this will be the correct number of pairs that will give us at most sum equal to upper. We return it, and this is the whole solution.